All right, welcome to chapter 2.1, a preview of calculus. All right, so kind of reading along here, but one of the big ideas, one of the big important things that developed calculus was the idea of the tangent problem. All right, how do you find the equation of a line that is tangent to a curve at any given point? So this purple line right here, we would say is a tangent line. It touches the red function right there at that spot. All right. And it doesn't really cross again, at least right around here. Yeah, it crosses again out here. But right in this zone, it's a perfect tangent. Meaning if you zoomed in on this point, the red curved function and the purple tangent line, they would almost appear to be perfect matches for each other if you zoomed in far enough. All right. A straight line, tangent line, and the curve, they would match really, really, really well. Okay. So tangent lines, in general, they're going to be really important for us. Okay, the derivative of a function, something that we're going to talk about a lot in chapter 3, is how we calculate the slope of that tangent line. Okay, and that is the big picture item of calculus 1, finding these derivatives, these slopes. Okay, so we can't just jump straight there. Of course, this is math. We kind of have to know how it works and why it works. So what we do, instead of going straight to these derivatives, these tangent line points, we start with 2 points. Okay. Now, 2 points on the same equation, if you draw a line connecting them, they're going to cross multiple times. You see this one crosses 3 times. Okay. At least 3 times, I should say. Maybe 4. Secant lines, compared to tangent lines, they're not as good. All right. They don't line up with our function nearly as well at this one point. Okay. So you should have learned this formula way back when. This is the slope formula. It's also called the average rate of change. Using the slope between any 2 coordinate points, all right, if we have this point and this point, we can find its slope. And then from that slope, we can create the linear equation. We did this in chapter 1 in functions. Okay. So what we're going to do is we're going to take a look at a function and a certain point. If you plug -1 into this equation, you get -1 cubed, that's -1, minus -1 squared, minus -1, that's +1, plus 2. -1 minus 1 plus 1 plus 2, that is a good old value of 1. So we have the coordinate point -1, 1. All right, so if we want to find a secant line, something like this, all right, what we do is we pick a point that's close. This was -1, so let's choose a point like -2. Now, this function and this function aren't exactly the same, but we'll get there later. So if I plug in -2, -2 cubed, that's -8. -2 squared, that's +4, but it's minus. Minus -2, and then just plus 2. Overall, that's what? -8. All right, general idea. If we now connect these 2 points, okay, with a straight line, that's called our secant line. To find the slope of that secant line, we do our slope formula. -8 minus 1, y minus y, over -2 minus -1, x minus x. So we have -9 over -1. That is a slope of 9. We can then use that equation, or use that slope, and that first coordinate point to make a secant line. Y minus y1, so y minus 1, equals m, x minus x1, minus negative, turn to positive, distribute that 9, and then add the 1. So 9 times 1 is 9, 9 plus 1 is 10. All right, using graphing software, let's graph f of x and its secant line. so as you can see, our secant line and our graph, they line up pretty good. It connects two spots on here, but if we just focus on this one point, our two graphs don't line up very well. If you zoom out, yeah, they line up pretty good. All right, it looks like a pretty decent approximation, a straight line to approximate a curve. But if you look at just this one spot, no, they don't line up super great. Now, what would be better is that instead of choosing a point that is so far away from here to here, what if we move this point to just be a little bit closer? All right, and that is the idea of calculus in general. We're going to move those 2 points so that they're almost perfectly beside each other. Now, we can't put them directly on top of each other. You can't find the slope between just one thing. So you just move them really, really, really close. Now, the idea of moving two things, one of them really, really, really close to the other, that's the basic concept of a limit. What happens when two things get really, really close to each other? And what happens? That is the perfect example of a limit. Okay, two things that can't be equal, or else our slope formula, that y2 minus y1 over x2 minus x1, if the 2 points are the same, we would be dividing by 0. Okay, so we make these two things really, really, really close, but not perfectly touching. And that will create the slope of our secant line. But these 2 points will be really, really, really close. All right, the closer they are, the more the graph will represent a tangent line. All right, and I've done this kind of sort of already in Desmos. All right, if we choose 2 points that are, far away like they were, it's not a great line. All right, but if we move these two closer and closer and closer and closer and closer, now this green line and our graph, they appear to be really good tangent lines. The closer it gets, the more like a tangent line it truly is. If I zoom in between these two, notice the red function and the green graph, the green linear equation, they're like perfect matches for each other for this little time period. All right, and that's the big idea that we're going for. We want our green linear equation to really perfectly match up with our red function around this point, this spot that we were starting with. Okay, now notice what happens when we make these two spots exactly equal. Our green graph disappears because our slope becomes undefined. You can't have the two spots exactly the same and make a slope. All right, the formula just doesn't work. But this thing of limits lets us kind of guess what would happen. See, our slope is like 4.04 when we're just a little bit on this side of our coordinate point. Or undefined if it's exactly equal, but when you pass it, it's 3.96. Well, that's right in between 4.04 and 3.96. Well, 4. Okay, so if we made our slope just a perfect 4, it doesn't go through this secant point anymore. This would just be the straight tangent line. Okay, and that is the general idea of calculus, trying to find these tangent lines, namely the slope of that tangent line. Now, the second big thing in calculus is here. Calculus 2, and really the end of calculus 1, is focused on these things called integrals, finding the area between a curve and the x-axis. Now, if you have this graph, y equals x squared plus 1, and you want to know the area between the curve and the x-axis. So from here to here, all the way up to here. Well, it's not a shape I know. I can't use an area formula that I know. So what we do to start off is we say, hey, I can just make little rectangles. I know the area of these rectangles, and I can find those areas really easily. Like this is a 1 by 1 rectangle, it's areas 1. A 1 by 2 rectangle, it's areas 2. A 1 by 3, not 1 by 3 rectangle. A 1 by 5 rectangle, 1, 2, 3, 4, 5. So my total guess for the area between the x-axis and the curve is 1 plus 2 plus 5. I think the area is right around 8. Now, clearly, that's not the actual correct area. There's all this missing stuff. So I think the area is actually a little bit more than 8. So if we didn't do this with just 3 rectangles, if we did this instead with 6 rectangles, I'd have to cut each one of these in half. Now go up and I'd hit my graph. Now you see how adding in these extra pieces, it kind of fills in some of that extra white space. And by doing this, so again, the goal is to get to there. By doing this, we fill in more of that white space. Now, these areas would be a little harder to find. I'm not going to take the time at this moment to do it. All right. But if we did 6 rectangles, we fill in more of that white space. Our answer would be a little bit better. If we did even more rectangles, it would start to fill in more and more of this white space. And we get a better answer. If we did even more rectangles, we fill in even more of this white space. The more and more and more rectangles you do, the closer and closer and closer you're going to get to the true area. Now, every time we made a new rectangle, we filled in kind of less and less white space. So eventually you would be filling in very, very small amounts of white space, and your answer would be kind of approaching the same thing. Like we got 8 this time, we might get like 8.7 the second time, and then like 8.8 the third time, and then 8.85, 8.9. We would keep getting these answers that are getting closer and closer and closer to something. And calculus is going to be the way that we kind of do this and how we figure out what it actually adds up to. Okay, we do that with something called an integral. Add up all these little tiny areas. All right, that's the end of Calc 1 and the start of Calc 2. But both of these two ideas, finding this tangent line and finding those areas, are going to rely on these things called limits. All right, now again, limits just talk about what happens as you move these 2 points closer and closer together. All right, what happens to that slope? Or as you add more and more and more and more rectangles, what happens to that area? Okay, and we'll define this more mathematically as we go, but that's the basic idea and where we're going, finding these derivatives and finding these areas.